Now, we'll study the electrical systems. The electrical systems include switching devices such as mechanics switches, example relays or solid state switches, examples diodes, thyristors, and transistors, where the control signals switches on or off some electrical devices, perhaps a heater or a motor. Solenoid types devices where a current through a solenoid is used to actuate a soft iron core. For example, the solenoid operates hydraulic or pneumatic valves where a control current through a solenoid is used to actuate a hydraulic or pneumatic flow. Drive systems such as DC or AC motors where a current through a motor is used to produce rotation. Now, about the relays. Relays are electrically operated switches in which changing a current in one electrical circuit switches a current on or off in another circuit. For the relay shown in figure, when there is a current through the solenoid of the relay, a magnetic field is produced which attracts the iron armature, moves the punch rod, and so closes the normally open switch and opens normally closed switch contacts. Relays are often used in control systems. The output from the controller is relatively small current and a much large current is needed to switch on or off final correction element. For example, the current required by an electric heater in a temperature control system or a motor. In such a situation, they are likely to be used in conjunction with the transistor because relays are inductances. They can generate a back voltage when the energizing current is switched off or when their input switch from a high to low signal. As a result, damage can occur in connecting circuit. To overcome this problem, a diode is connected across the relay. When the back EMF occurs, the diode conducts and shorts it out. There are a number of solid static devices which can be used electronically switch circuits. These include diodes, thyristors, and triacs, bipolar transistors, power MOSFETs. Now, the diodes. The diodes has characteristic shown in the figure. A significant and so allows a significant current in one direction only. The diode can be regarded as a directional element. Only passing a current when forward biased, that is, with the anode being positive with respect to the cathode. If the diode is significantly reverse biased, that is, a very high voltage, it will break down. If an alternating voltage is applied across the diode, it can be regarded as only switching or when the direction of the voltage is such as to forward bias and being off in the reverse biased direction. The result is that the current through the diode is half rectified to become just the current due to positive halves of the input voltage. Now the next one is transistors and tracks. The transistors or silicon controlled rectifiers can be regarded as the diode, which has a gate controlling the conditions under the diode can be switched on. Figure shows the transistor characteristics. With the gate current 0, the thyristor passes negligible current when reverse biased. When forward biased, the current is also negligible until the forward back down voltage is exceeded. When this occurs, the voltage across the diode falls to a low level, about 1 to 2 volt, and the current is then only limited by the external resistance in a circuit. Thus, for example, if the forward breakdown is at 300 volt, then this voltage is reached. The thyristor switches on and the voltage across it drops to 1 to 2 volt. If the thyristor is in series with the transistor 20 ohm, then before breakdown with capability of a thyristor is high. And thus it is widely used for switching high power applications. The triac is similar to thyristor and is equivalent to a pair of thyristors connected in reverse parallel on the same type. The triac can be turned on in either forward or reverse direction. Now, the figure shows the type of effect that occurs when a solenoid alternating voltage is applied across a thyristor or a track. Forward breakdown occurs when the voltage reaches the breakdown value, then the voltage across the device remains low. Now, the solenoids. The solenoids is used translating on or off electrical signals to on or off mechanical movements and normally used as a linear actuator. A solenoid valve finds the application in control of room heating, gas flow, water flow, etc. You can see in the figure, the solenoid is made up of a coil with a movable iron core. The coil will have some voltage or the current rating may be DC or AC. A typical circuit is shown in the figure B. When the coil is energized, then the core is pulled inside the coil, and the amount of force by which the core is pulled mainly depends upon the number of coils and the amount of current flowing in the circuit. The cutaway section is shown in the figure, illustrates the operation of solenoid actuator. The spring return plunger is held in the upper position when the coil is electrically de-energized. When the voltage is applied to the electrical coil, a magnetic field is produced in the solenoid frame. The frame is essentially the permeable magnetic laminations excited by the coil. The plunger is actuated by the magnetic field, pulling it down the position against the spring pressure. The choice of solenoid for an application depends upon the size of the mechanical load, the moment, the distance of plunger, the type of electrical connections, the type and value of the current and voltage. Now, the AC or DC motors. The electric motors are used as the power sources in variety of mechatronic applications. Therefore, the electric motors often feature as prime movers in the variety of driven systems. They can either be classified on the basis of functionality or electromagnetic characteristics. There are different types of electric motors: permanent, electromagnetic. There are different types of AC motors, that is single phase induction, synchronous, polyphase, induction or synchronous, and stepper motors. That is the third one. Permanent magnetic type, variable in reduction, reluctance, and hybrid type. This figure, you can see the construction and components of a electrical motor. Stator is the stationary outer or inner housing of the motor that supports the material that generates the appropriate stator magnetic field. It can be made of permanent magnets or coil windings. Rotor is the rotating part of the motor. Depending upon the constructions, it can be permanent magnet or ferromagnet cores with the coil windings to provide appropriate armature field to interact with the stator field to create the torque. Field coil is the portion of the stator that is responsible for generating the stator magnetic flux. Armature is the rotating winding that carries the current and induces a rotor magnetic field. Air gap is the small gap between rotor and the stator where the two magnetic fields interact and generate the output torque. Brush is the part of the DC motor through which the current is supplied to the armature. Torque is produced by an electric motor either through the interaction of the armature current and the stator magnetic field through the interaction of the stator field and the armature field. Thank you.